All this was required in the context of this course simply and precisely to make the point that light waves are also propagating waves, and they propagate as fields, as we will see soon. And light waves do not particularly require a medium for propagation like material waves do. It is something you may have already encountered in your studies or even in popular science. So, a phenomenon that describes the a wave of light in one dimension must again be an equation which has the form of the wave equation. If E is the electric field of a light wave, light is, as you must have learnt earlier, light is an electromagnetic wave or an EM wave in short. We will mostly talk only about the electric field of the electromagnetic wave, although it is electro and magnetic, for reasons that I will explain to some extent later. So, the electric field of the light wave, which is the quantity that oscillates in space and time, is prominently given the symbol script E or E in this course and in a lot of popular textbooks that are used in physics and engineering curricula. So, this quantity, which is a real valued quantity E, essentially becomes the argument in the wave equation, and a one dimensional light wave is essentially described by this wave equation, which is again d2E by dx2 multiplied by mu and epsilon, a product of mu and epsilon, and more importantly d2E by dt2 is equal to 0, right. Mu and epsilon are properties of the medium in which the wave of light is propagating. Epsilon is the permittivity of the medium and mu is the permeability of the medium in which the light wave is propagating. Although a light wave does not necessarily need a medium to propagate, of course we know that light waves can also propagate in media provided they are sufficiently transparent, such as glass, right. So, now let us consider the one dimensional wave equation for light waves. Now that we have the wave equation for light waves written down, the simplest solution for this wave equation, in this case for light waves and in other cases for whatever wave as the case may be, comes about by the use of trigonometric functions, the sine and cosine functions, and we can describe in a very precise way a wave of the kind that we just looked, which propagates on and on and on without particular losses or distortions or whatever at a given frequency and wavelength, which we will soon define as quantities of spatial and temporal periodicity, using these two functions, that is the cosine function and the sine function. Okay. So, this solution for the wave equation, which is the one dimensional equation for a light wave, where the electric field E of xt is described by a product of B, a constant, times cosine of x plus or minus Vt, but note here that this is multiplied by a constant or a parameter k. This is one piece to the solution that we are considering now, plus C, again a constant, times the sine of again k multiplying the x plus or minus Vt form. This is a fairly general description of a wave, and we have gone a step forward from what we considered earlier to be some general function of the form f of x plus or minus vt. Okay. Now the wave that we are considering has become more real, and we have given a context to it, that is, this is a light wave, right. But then we have done something different and important over here, and for the first time we have introduced the parameter k over here. So, k is first of all a constant. Now we can unwrap the meaning of this constant in the context of another parameter which is very important in the description of this wave, which is v, which is the velocity of the wave. Velocity is a vector. This is the amplitude, this is the resume. So, now in considering the electric field solving the one dimensional wave equation for light waves, that is E of xt of this form, b cosine k multiplying cosine of k multiplying x plus or minus vt plus c sine of k multiplying x plus or minus vt once again. Here we have introduced this new parameter k, which is primarily a constant. There is a physical meaning to k and what comes thereafter due to its introduction, which we will unwrap in this context, also noting the fact that v is the velocity of the wave, it is the magnitude of the velocity vector, that is, and this magnitude is also greater than 0, right. So, now let us understand what we have done to the solution of this wave. We now multiply out what is in the argument to realize that we have here kx plus minus kv multiplying t, right. Therefore, E of x comma t is now the constant amplitude factor b multiplying cosine of kx plus minus omega t plus c multiplying the sine of kx plus minus omega t, right. Now, what is omega? Omega clearly is now a new parameter that we have defined using v and k. Omega is essentially the product of v multiplying k, or omega by k is equal to v. Okay. And since we already know that the parameter or the coefficient of the second derivative of the wave amplitude function with respect to time is 1 divided by v square, we further realize that v is essentially 1 divided by the square root of the product of mu epsilon in this case, which is the product of the permittivity and permeability of the medium. But then what is the meaning of these quantities, that is k, v and omega? This is what we will want to understand much better, and we will dedicate a bit of time for that. Before that, let me connect this to something which we all know very well, that is the speed of light, or in particular the speed of light in vacuum. So, the speed of light in vacuum is a very special quantity, especially for physicists, and the name Einstein should immediately pop up in this context, right. The speed of light is a universal constant and has approximately this value of 3 times 10 to the power 10 centimeters per second, or 3 times 10 to the power 8 meters per second, right. Here the coefficient 3 is approximate, it is 2.9 something, a long number which has actually been measured to immense or very high precision in experiments. So, we should ideally treat this with a lot more respect than just round it off to 3. But then this is a universal constant, as we know from even elementary considerations and knowledge of special relativity. We often also hear the notion that nothing can travel faster than the speed of light, and so on and so forth in both popular and public science, say lectures or media, which is quite true. This is nature's speed limit, the speed of light in vacuum. So, this velocity is essentially 1 divided by the square root of 2 parameters, the permittivity and permeability, making the product under the square root sign. If this is the case of vacuum, then the permittivity and permeability of vacuum need to be substituted, and often in that case epsilon becomes epsilon naught or epsilon subscript 0, and mu becomes mu naught mu subscript 0, right. So, that essentially connects us to a whole lot of conceptual knowledge and notions that we have picked up so far. Okay, now I have still not fully unwrapped the meaning of K and V, K and omega in this context. We understand what V is rather. But before doing that, let us proceed further, and since we have brought things up to speed with these trigonometric functions, that is cosine and sine, we can actually do something very nice using further trigonometric identities and write down this entire expression which had a sine plus a cosine in the following way, using this nice trigonometric identity concerning the cosine of two variables. Here let us call the two variables z and y. Cosine of z minus y, where the argument is z minus y, is cosine z multiplying cosine y plus sine z multiplying sine of y, right. So, earlier we had a form of b multiplying the cosine of a quantity plus c multiplying the sine of a quantity, right. So, we are going to exploit this trigonometric identity and show that the previous form of E of x comma t, which we learnt about, has this very simple form, which is a, an amplitude coefficient, multiplying the cosine of kx minus omega t and another parameter theta, which does not depend on x or t, right. So, here in the trigonometric identity which I have just used, let us set z to be equal to kx minus omega t, and let us set y to be equal to the theta. As I said, theta does not depend upon x or t. Then, using this trigonometric identity, cosine of z minus y is equal to the sum of a cosine term and a sine term. We can write this down in the following way: E of x t is a multiplying cosine of kx minus omega t multiplying cosine of theta, theta again is independent of x or t, plus a multiplying the sine of kx minus omega t multiplying sine of theta. Now, compare this to the form of the solution we had earlier, which was E of x t is equal to a b, a constant, multiplying kx minus omega t plus a c multiplying sine of kx minus omega t. Comparing these two equations apple to apple, that is a cosine kx minus omega t multiplying cos theta plus the second term, b cosine kx minus omega t plus the second term. We then tease out the relation that a multiplying cosine of theta is just what we used to call b, and A sine of theta is what we previously called as C. Therefore, the important point is that the two forms of solution which we considered and compared, that is E of xt being b cosine kx minus omega t plus c sine kx plus omega t, and this new form E of xt being a cosine of kx minus omega t minus this parameter theta which is independent of x of t. These two forms are equivalent mathematically. Therefore, here and hereafter we can simplify the writing of the solution using this form of the equation where E of xt is equal to a, an amplitude factor which again in the present discussion does not depend on x or t, multiplies cosine kx minus omega t minus, retake, restart. Therefore, here and hereafter we can essentially use this compact form of the solution, that is E of x comma t is equal to a multiplying a cosine term whose argument is kx minus omega t, which is reminiscent of the x minus vt term, minus a theta. All of this has physical meaning which we can explore in the coming view graphs.